you so much, Fred. Lovely. Does this mean I can go home now? Well, thank you so much for coming out on such a cold day, and I hope that we can warm people up by talking about a hot topic, and that is starlight in the universe. And we already have an appreciation for the power of stars. Stars produce a lot of energy, and in fact, almost all of the energy that we use in our daily lives here on Earth comes from a star, and that star is the sun. So there are many stars in the universe, and we can start by talking about stars in general. Stars on an astrophysical scale are actually fairly simple objects. There's simply this balance between gravity, the energy of gravity pulling inward, and then the nuclear energy that's burned at the core of a star converted to radiation pushing outward. So just gravity pulling inward and nuclear energy pushing outward. And so the balance of that is what a star is. And so basically, stars are driven by one fundamental property, and that is their mass. It's the weight of the star crushing the core right at the center of a star that drives the rate at which the energy is produced. So it's the weight of the star crushing the core that drives the rate of nuclear burning. And hence the star's luminosity depends upon essentially the weight of the star, the mass that goes into that star, and how much weight it has on the core. So a low mass star tends to burn more slowly because it has less weight. And so the lifetimes of the low mass stars are very long. The sun, for example, is a low mass star. These low mass stars are cooler, they're red and yellow in color, and so the sun has a very long life expectancy. Its total life expectancy is about 10 billion years. It's about halfway through that right now. So the sun is already pretty old, 5 billion years old. The lowest mass stars have even longer life expectancies because they're even lower mass than the sun. So they burn at a much slower rate. And so the life expectancies for the lowest mass stars are 10 times longer than that of the sun. They're about 10 to the 11 or 100 billion years. And so if you think about the fact that the universe is only 14 billion years old right now, these stars literally live forever as far as our current cosmic timescale. Their lifetimes are 10 times longer than the current age of the universe. So the low mass stars really live for a long time. They burn very slowly, and they have colors that are reddish or yellowish. This is a globular cluster that you see in this image, and it has pretty much just red and yellow stars, as you can see from their colors here from the Hubble Space Telescope. Most of the globular clusters in our galaxy are very, very old, and those stars have managed to survive for that long. On average, when you see a low mass star, because their life expectancies are so long, you pretty much expect that on average they're already old by the time you see them. And that applies to the star that's outside right now. So it's 5 billion years old. It's already quite old. It's 1/3 the age of the universe. Let's contrast that now with the hot blue stars. These are blue because they're very, very hot, and they have very short lifetimes. The mass of these blue stars is so high that the core in the very center is just simply crushed, and therefore the nuclear burning rate occurs at a much higher rate. And so we have very, very luminous stars for these high mass stars. Their life expectancies are only about 10 million years. And for the very, very most massive stars, they're as low as 3 million years. So you may say, okay, 10 million years, that still sounds like a really long time. But remember that it's 1,000 times shorter than the lifetimes of the more massive stars, less massive stars like the sun. The sun has a life expectancy of 10 billion years, whereas these high mass stars have life expectancies of 10 million years. So that's 1,000 times shorter. And to put this into perspective, as I mentioned, the highest mass stars have life expectancies of 3 million years. On the Earth, 3.2 million years ago, there was not only life, there was not only mammals, but even our own ancestor, a hominid, Australopithecus afarensis, named Lucy, walked the Earth. So in the time that Lucy existed and the present day with ourselves here, one of these massive stars could have come and gone. So on a cosmic time scale, these massive stars are simply the blink of an eye. They have very, very short lifetimes. And you can see that they are blue in color, they're very hot, and they're extremely luminous. So for these massive stars and these low mass stars, you can distinguish them quite clearly from the colors that they have. And the big stars burn hot and blue, and bright and fast, and the small stars burn cool and red, and faint and slow. And mass, as you can see, is the property of these stars that really matters. Mass matters. So what's going on with the different colors that we have here? You recall that light is a form of energy. In fact, let me demonstrate that first. Light is a very useful form of energy. As I mentioned, all of our energy here on Earth pretty much comes from the sun. And what I have here is basically a very simple telescope. We've got one mirror here, and we've got another mirror all the way across the room there. And I have a light bulb. So let me just show you this light bulb. Just a plain old incandescent light bulb that you can see. Okay? And it's shining over there. And I'm just going to put this, well, let me see here. Is that aligned okay?
Yeah, that's good.
Okay. And I'm just going to put this back on here so it doesn't blind us. And all I'm going to do is I'm going to turn up the power on the light. So this is an ordinary light bulb. And all the way across the room, we saw it light whatever's burning down at that end, right? So light truly is a form of energy. It's a very pure form of energy. Over here, I have something maybe a bit more familiar to you. It's a photovoltaic cell, okay, that we have right there. Just like a solar panel, essentially. I guess I'd better not cover it. And we have a little gadget hooked up to it. And this is a lamp. This is a fairly high energy lamp. It's ultraviolet. So if I turn this on, we can get our little gadget to go. So it's simply the form of light energy that we have coming from this lamp that is producing the electricity to make that little rotor go. So I can cover it up, and it stops turning. So light is a form of energy. And you remember that white light can be split up into different colors. So we're talking about the colors of the stars. And I can turn this on. And right over there, you can see a beautiful spectrum. The spectrum is simply the white light that is broken up into its component colors. We see red on the left, we see blue on the right, and the different colors correspond to the different energies of that type of light. Light is kind of confusing because it's kind of counterintuitive. It behaves as both a wave and a particle at the same time. So we talk about the different colors of light in terms of different wavelengths. Blue light is very energetic. It has a short wavelength. Red light is less energetic. It has a long wavelength. So the light on the left there, which is red, has lower energy than the light on the right, which is blue. So the blue light is more energetic than the red light. This is just a part of the electromagnetic spectrum. Light is electromagnetic radiation. Those two things mean the same thing. And we just see the part that our eyes are sensitive to. There is more light to the left of that swath of color that you see. Infrared light and radio wavelengths that extend further to the left. And on the right, we have higher energy light, ultraviolet light, and X-rays and gamma rays that would extend further to the right. And our eyes simply aren't sensitive to that. So knowing that we just saw a correlation here between the temperatures of stars and the color of light that they emit, you would then infer that hotter stars, presumably, are bluer in color because they correspond to higher energy wavelengths of light. And that's exactly what the case is. We can see this demonstrated more graphically with this little gadget. So here again, we have a light bulb, okay, the same kind that we had over there. I'll just turn it on a little bit for starters. And you can see that it's just a plain old light bulb once again. Everybody can see that? Okay, so I will just put this here again just to shield your eyes for when it gets bright. And what we're seeing in this graph, if we can see it, is a spectrum. It's like what I just showed you on the wall here, but this is a graphical demonstration of the spectrum. We're seeing wavelength on the x-axis, and it's in nanometers. A nanometer is 10 to the minus 9 meters. So we see that the long wavelengths are on the right. That means red is on the right, and the short wavelengths are on the left. So blue is on the left side. Blue is 400 nanometers. Red is like 700 nanometers. Okay. So what we're seeing with this light turned on, and you saw a moment ago, it's still turned on right here, is the spectrum of light that's emitted by this light bulb. And we can see that its peak is maybe somewhere around here. Okay, I'm marking that with the green line. So that means that the main color that we see from this light bulb is basically in the near infrared. So we can't quite see that with our eyes. We're just seeing the visible light here from this light bulb. And so that is at about 770 nanometers or something like that. Now, if I turn up the power, you will notice that the color, and from here you'll want to watch the color that's reflected on this white board because it's so bright that I'm not looking at it myself. And you can see from the color of the board that it's actually changing its color, isn't it? And so let me change the scale here. Where did the little scale thing go? Here we go. So we changed, oh my goodness, it's flat. Totally peaked out. Let me turn it down a tad. There we go. So it looks like it's saturating the detector. And you can see that the peak has moved way to the left, right? The peak is now closer to about 630 nanometers or something. So it has moved to shorter wavelength is the point, right? It's moved toward a bluer color, and you can actually see with your eyes here that the color on the board is much bluer than it was a moment ago. So literally we are seeing that the color of this has shifted to shorter wavelengths. So there is a correlation between the temperature of this filament and the color of the light that it emits. Okay, so another thing, going back to the, my slide here, was talking about stars. Let's consider that this filament right here is actually 1 square centimeter on the surface of a star, okay? Right now, and it's gone back to being a very reddish, orangey color, as you can see. Right now, it's a fairly cool star, a star whose temperature may be something like 3,000 degrees Kelvin, which is the same as centigrade, more or less. And you can see that it's also fairly faint. If I turned it up, you could see how incredibly luminous it's getting, right? And we've maybe doubled the temperature now. And it's so bright that we can't even look at it. Okay? This is still the same square centimeter on the surface of a star. And so real stars do this too. All of what I've shown here applies basically to any kind of thermally emitting body. And stars are perfectly normal thermally emitting bodies. So what we have is that the surface of these stars, square centimeter by square centimeter, is also that much more luminous for only a small increase in the surface temperature. That is dramatically demonstrated in a very famous diagram from astronomy called the Hertzsprung-Russell diagram. And it's plotting here the temperature that you can see on the x-axis. Unfortunately, the x-axis is backwards for historical reasons. Hot goes to the left instead of to the right. But you can see that the x-axis is linear in scale, more or less, or that anyway covering a much smaller range. And then on the y-axis, you can see a very, very large range in scale. So look at the sun right here, for example. The sun is almost 6,000 degrees Kelvin and it has 1 solar luminosity. If we merely double the temperature of the sun to, say, 12,000 degrees, look at where these stars are. And the stars all live here on this main sequence of stars. The stars that are double the temperature of the sun have luminosities that are over 100 times the luminosity of the sun. So just for an increase of a factor of 2 in the temperature, we've increased the total luminosity of the star by over a factor of 100. So the luminosity and the temperature don't scale directly at all. The luminosity just goes right up. And you saw exactly that happening with this light bulb. So the stars work exactly the same way. And therefore, these blue stars, which are very hot, you can imagine how incredibly luminous they are. And indeed, they are the powerhouses of light in the universe. And they also produce very, very hot radiation. Their radiation peaks not in the yellow, like the sun, but in the ultraviolet. And ultraviolet, as we saw a moment ago, is much more energetic radiation than visible light. It gives us sunburns, it causes cataracts, and it does all kinds of nasty things. So these massive stars are a significant source of radiation energy in the universe. They are the most massive stars, 100, 150 times the mass of the sun. They have luminosities that go up to 1,000,000 times the luminosity of the sun. They're very hot, being about 8 times the mass of the, 8 times the temperature of the sun. And they have very short lifetimes, as we talked about, 1/1000th the lifetime of the sun. Just for some added drama, they are also very dramatic when they die, and they explode at the ends of their lifetimes, which is not something that the sun is expected to do. Okay, so with all of that incredible amount of ultraviolet radiation and vast quantities of it, what does that do to the environment? So let's talk about the environment of these hot blue stars. They don't live for very long, and therefore they're still, even by the time they die, usually still very close to some of the interstellar gas out of which they formed. Because they are so hot and ultraviolet, they heat up the gas clouds around them, and they cause them to glow with this characteristic red color. I'll talk more specifically about that in a minute, but first let's talk about the environment of these stars. So what we see is this characteristic red color that comes from hydrogen, and these stars are responsible for creating these beautiful nebulae, some of the most beautiful pictures that we have in astronomy. So stars live within galaxies. Galaxies, as you may know, are kind of like the building blocks of the entire universe. Our sun is one of 10 billion stars in our Milky Way galaxy. Galaxies are made up of stars and gas, and in particular, dark matter, which I won't say too much about, but dark matter is basically the primary component out of which galaxies are made. It has about 10 times more mass in dark matter than in stars and gas. So the stars and gas and visible things that you see in galaxies are more or less just the frosting on this vast dark matter halo that a galaxy is really made of. But in the meantime, looking back at the ordinary visible matter that we can see in this image, this is a beautiful star-forming galaxy, NGC 6946, and we can immediately see where the blue stars and where the old stars are located. So we can see that the old stars, which are yellowish and reddish in color, are located more toward the center of this galaxy. And then instead you see the bluer light coming from the outer disk of the galaxy. In the outer disk, you also see that it's studded with all these red nebulae of the kind that I just pointed out, which are lit up by the hot blue massive stars that are still within them. Here is another galaxy. This is the Andromeda galaxy, our next door neighbor. And our Milky Way is fairly similar to the Andromeda galaxy, except that this galaxy does not have a very high star formation rate. So you can see that there aren't very many of these star-forming clouds, the red blobs, throughout the galaxy. You do, however, see that it has a very large yellowish bulge in the middle. So we know that that's where the low mass old stars of that galaxy reside. And then here is another galaxy. This is basically one which is made entirely out of only these very, very old low mass stars. It's kind of reddish in color, very smooth in appearance, no gas whatsoever. So this is a giant elliptical galaxy. So those are basically the kinds of galaxies that are out there in the universe. And then our own Milky Way is thought to look something like this. It's a spiral galaxy like the Andromeda galaxy, but it has a higher star formation rate. So you see a lot more of these red nebulae throughout the arms of our Milky Way. But like the other galaxies, it has a central yellow bulge made of old stars. And our galaxy also has a bar-like feature across the middle of it. Our sun is located something like 2/3 of the way out from the center of our galaxy, which is toward the direction of Sagittarius. So if you want to look toward the bulge of our own galaxy, look toward Sagittarius in the summer, and you will be seeing basically more or less the center of our galaxy. Galaxies, as I mentioned, are sort of like the frosting on all of this dark matter in the universe. And there's a beautiful simulation here that is based on real data, just to give you an impression of what the universe is like beyond our galaxy. So all of these points of light here are individual galaxies. And the more you look at this, the more you realize that there's actually a structure to the way the galaxies are organized. They're kind of in filaments, and at the nodes of the filaments of this web, you can see clusters of galaxies. Again, this is based on actual data from the Sloan Digital Sky Survey. So that is the universe outside of our galaxy. There's a lot of dark matter. Again, the dark matter is invisible, and the galaxies are just kind of marking the location where the densest regions of dark matter are located. But you get this sort of sense of a cosmic web there. So back to looking at the immediate environment of the massive stars. The massive stars light up these nebulae. What exactly is going on here? Well, these are the hot, young blue stars that have a lot of ultraviolet radiation. And what happens is that this radiation is responsible for doing what we call ionization. Ionization just means that you have some source of energy, perhaps a photon like this, a high energy photon. This should actually be an ultraviolet photon, and that it might be capable of popping the electron off of a hydrogen atom. So you remember that hydrogen is the simplest atom in the universe. It is just a proton, which is positively charged, and an electron, which is negatively charged. Normally, they like to live together, attached to each other. They love togetherness because opposites attract. And once in a while, if the electron gets very excited, as we say, it can actually become so excited that it's popped off from its proton. How does that happen? It has to receive energy. And one way of doing that is by zapping it with a high energy photon. It can't be a low energy photon. It must be above a certain threshold. It must have a wavelength that's at least as short as 91 nanometers. So here is my ultraviolet photon. Here it comes toward the hydrogen atom, and it has popped off the electron. And now my photon is gone, right? The photon's energy was used up in popping off the electron. We call this ionized hydrogen now. It's just a proton, so it's ionized hydrogen. If we had helium and we popped off one electron from helium and it still had an electron, that would still be called ionized helium. Okay, so I mentioned that they like togetherness. So they may want to come back together again. They always want to come back together again. Okay, so it's very excited. It has a lot of energy. It has to calm down in order to rejoin its proton. So how does it calm down? It has to give up energy, right? So if it's going to give up energy, it can do so by emitting a photon, okay? It's giving up energy. This photon is the characteristic red color that we see from all these hydrogen atoms. The red photon is the recombination of the hydrogen atom. To make a long story short, it comes out at this very specific red color. And so that is why these hydrogen atoms always have that specific color when they are recombining. And so this is the signature of recombining hydrogen atoms in the universe. So the immediate vicinity of these massive stars, they have enough ultraviolet radiation to cause the atoms to become ionized and then to recombine again. The recombination happens by itself. It's really the ionization that takes energy. So I'm just going to put this on the board so you remember it. There's a proton and an electron. When they're together, we call them neutral hydrogen because positive plus negative is neutral, right? If we make another one here without the electrons over here somewhere, we call this ionized hydrogen. And I will be referring to neutral and ionized hydrogen a number of times, which is why I put it on the board. Okay, so in the immediate vicinity of these massive stars, we often see clouds of ionized hydrogen gas. It has this characteristic red color that I showed there, and that comes specifically from the recombining hydrogen. So we know that this cloud is ionized, continually being ionized and recombining because of that red color that we see from the hydrogen atoms. The cloud that's above, that looks bluish, is not ionized. It doesn't have that red color. It's bluish because it's actually reflecting the light from a blue star that's in there. But that blue star is not quite blue enough. It's not hot enough to actually ionize the hydrogen gas. So the cloud that we see above that looks blue is merely scattering the starlight. That's just a reflection nebula, as we call it. The lower cloud, which looks red, is ionized, and we know that from the color of the hydrogen gas that we see there. So essentially, the star that's in the lower cloud is hotter than the cloud that is in the blue cloud up above. So one of the direct effects of these massive stars is that they ionize the clouds of hydrogen. This is very harsh radiation, so it's very energetic. So why should we care about ionization? Well, it turns out that our sun is located within what's called the local interstellar cloud, the LIC, and that the local interstellar cloud is actually partially ionized. In fact, mostly ionized. It's 2/3 ionized and 1/3 neutral. And here's just a little schematic of it. The sun is moving with respect to the local interstellar cloud at a velocity of about 26 kilometers per second. So we haven't always been in this cloud. We just kind of pass through different wisps and clouds throughout the history of our star. So our sun produces a solar wind. This solar wind produces a small stellar wind bubble that we call the solar wind bubble or the heliosphere. We know that the sun has a solar wind because we can see every time comets come by, for example, that the tails of the comets are pointing away from the sun. The comets are wind sucks that tell you which way the solar wind is blowing, and the solar wind is always blowing away from the sun. So that they're very handy that way. So essentially, the sun's solar wind bubble is a very small bubble. It's still confined within our own solar system because the sun's solar wind is very weak. In the upper left here, I'm showing you the stellar wind bubble of a massive star, which has an incredibly strong wind. Those produce stellar wind bubbles, which are on the order of tens of light years across, whereas the one for our solar wind bubble here is still, as I mentioned, within the confines of our solar system, only maybe a few light days or a few light weeks across. So our solar wind bubble is tiny. The exact dimensions are shown right here. 1 AU, an astronomical unit, is the Earth-Sun distance. And the inner edge of the solar wind bubble, which is this inner shell that you see right here, is about 80 times the Earth-Sun distance, 80 AU. The outer edge of the bow shock that you see out here might be about 200, 250 astronomical units, Earth-Sun radii. So it's a pretty small solar wind bubble, but the size of it does depend upon the strength of the solar wind. And that, in turn, depends somewhat upon the climate, the climate that's outside the solar wind bubble, so the ambient interstellar environment, how dense it is, how many neutrals it has. So in particular, let's say that I am a solar wind ion. The solar wind, by the way, is ionized because it comes from shock-heated gas. So it is not neutral, it is ionized. So here I am, I'm a proton. I'm one particle of ionized hydrogen moving toward a hydrogen atom that's neutral somewhere in the solar system. And I encounter this neutral atom, and I'm like, aha, an electron. I think I'll take this electron. So I was moving this way, and I take the electron. This interaction takes some energy. It's like a collision. And so I was moving in this direction. Now I'm no longer moving in this direction, and I've become neutral. And this thing has now become ionized, right? This is now the ion, and it is moving in some other direction. So the directionality of the solar wind has been altered by this charge exchange reaction that we've just had. And so that means that the solar wind is effectively not as strong because of this charge exchange reaction, and therefore it won't be as available to pump up the solar wind bubble. We have some numbers right here where you can see that if the ambient density, meaning outside of the solar wind bubble, if the ambient density increased, the value of 0.2 neutrals per cubic centimeter is what we have now, and that if it increased by, say, a factor of 5 to 10 atoms per cubic centimeter, that the inner boundary of the solar wind bubble would decrease by almost a factor of 10, as you can see here. So the solar wind bubble would shrink dramatically just with an increase of about 5 in the ambient neutral density of our environment. And that means that the neutral hydrogen density within our solar system at the radius of the Earth, which right now is about 0, would turn out to be a significant value, about 2 neutrals per cubic centimeter in that scenario. So our interplanetary climate would change significantly. And this could certainly have some effects on the Earth. We've seen that the solar wind momentum would be reduced. We see an increase in the anomalous cosmic rays, and by those are simply the protons that have been left behind by the charge exchange reaction. We'd see a lot of these just charged particles hanging around the Earth. And that would certainly affect the atmospheric chemistry as well as the conductivity of the Earth's atmosphere. So I'm an astronomer. I don't know anything about climate science, so unfortunately I can't even speculate about what that would do to the Earth, but you might find out more from the speaker next week. So that's one reason why we might be interested in the ionization state of the local interstellar cloud into which the sun is moving, and out of which the sun will be moving sooner or later. Moving back to the immediate environment of the massive stars, we've talked about how they ionize the gas clouds that are right around them. And this is a beautiful example from the Hubble Space Telescope. We called this the double bubble. And then over here, we see another galaxy. This is the Triangulum galaxy, another one that's very close to our own Milky Way. And we can see that it has lots of these ionized clouds of hydrogen, these red glowing clouds. And there are some that are very large, while there are others that are much smaller. And all of these tell us about how stars form in galaxies. So they're interesting just in and of themselves, how many there are, how big they are, what their luminosities are, and so forth. But besides these clouds that are ionized directly in the environment of the massive stars, we've also started finding that there's a lot of this diffuse gas between all of these clouds. And you can see that in this image right here. This is our own Milky Way. So this is a very large region of the sky that's shown here. And all of these are tiny labels. These are impossible to read, but they're like tiny labels of familiar parts of the sky. So these are all the normal star-forming gas clouds, which are ionized. This is all that red color, once again, even though it looks slightly different in shade here. And big gas clouds down here. But if you look between them, you can see a lot of this diffuse light. All of this diffuse light also appears to be photoionized, as we called it, ionized by the ultraviolet radiation. We weren't 100% sure where that ultraviolet radiation might have come from. Again, we would have thought this might come from massive stars, but if the massive stars are busy ionizing their immediate gas cloud, is there actually any UV radiation left to ionize stuff that's so far away from these gas clouds? If we look at other galaxies, we can see something similar here. This is an edge-on galaxy shown in the same hydrogen light, which would look red if it were in true color. And what we're showing here are these blobs. And we've taken a computer program which will figure out for us where the boundaries of these clouds are. And then we've digitally subtracted them. So the nebulae have been subtracted in the bottom image here, and lo and behold, you see all of this diffuse warm gas again. So that's the warm ionized medium again of that galaxy. So how the warm ionized medium is powered has been another one of these mysteries that we've been working on for some time. Well, so in my research group, we've figured out a way to kind of examine this more carefully. One of the big questions is whether these nebulae that we've seen, the star-forming nebulae, are actually transparent in the ultraviolet, right? Because if those clouds are transparent, that means that some, maybe a lot, of the UV radiation would actually be able to escape to very far distances and be available to ionize the diffuse gas in the pictures that I just showed you. Well, so the idea here is basically to use what's called the ionization structure of a nebula. You would think that close to the massive star, let's say over here, we have the stars. These are the ionizing sources, the hot UV emitting stars. Close to the stars, you might have a region, a zone, that is highly ionized. This is doubly ionized oxygen that I'm showing there, but it doesn't even have to be oxygen. Let's just say that it's a highly ionized zone. So I'll put 2 pluses there for highly ionized. You might have knocked off more than 1 electron. You might have knocked off 2 electrons, right? Because you're being bombarded with a lot of UV radiation. So missing 2 electrons here. If you have plenty of gas that is available to basically suck up all of the radiation that's produced, then you would travel to a region out here that is less ionized. And then finally out here to a region that's neutral. So if you just basically have an infinite amount of gas, you would expect to see this kind of ionization structure. The UV sources are here. You have highly ionized zone here. Then you have a less ionized zone, and then you have the neutral zone out here. That seems pretty straightforward, right? So if we were able to actually trace the highly ionized and the neutral regions, we would be able to tell whether these clouds are transparent or not. Because if the cloud is transparent, then you wouldn't have these 2 regions. So for a transparent cloud, you would maybe have only the highly ionized region and then not have these regions. So hopefully that seems sensible here. I can put this if you want. That you're not showing a transition zone to this intermediate low ionization region. So this one is opaque to the UV radiation, and this one is transparent to the UV radiation. In the pictures that I'm showing you here, you can see the low ionization species shown in white. This is singly ionized sulfur, and the high ionization species shown in black, doubly ionized oxygen. So in the center of these regions, we see they're very close to the stars, and they are in a region that's highly ionized, very exposed to the UV radiation. These are regions that are opaque. We see that they have envelopes of white, which correspond to the low ionization transition zone, to the neutral. So out here is neutral. This is the low ionization envelope, and then we have the high ionization region right in the center. And then this, by the way, is the telescope with which these images were taken. It's down in Chile. It's the University of Michigan's Curtis Schmidt telescope, named after H.D. Curtis, a famous astronomer, Michigan professor from the early 20th century. Contrast the pictures of these nebulae now with these. Notice that we see on the left side that the high ionization region has no envelope, no blanket of the low ionization region on the left side. Whereas on the right side, it does have the transition to the low ionization zone, which is white. So it's opaque going toward the right, and it's transparent going to the left. So just by looking at these images, you can see whether they're transparent or not in the UV. And this is a picture of my former postdoc, Eric Pellegrini, who led most of this work. So if we want to know whether a lot of these ionizing photons are actually escaping into the interstellar medium at large, we can look at the individual nebulae that are in these galaxies and see how many of them are transparent and how many of them are opaque. And so that's what we're doing with this picture right here. This is a region of a galaxy, just a blow up on a complex area. And you can see that most of these regions have white envelopes, meaning that they're essentially opaque to the UV radiation. Whereas this one, N44C, is clearly transparent. So it looks very black. It does not have a white envelope around it. We see maybe a couple other regions that look like they're showing some exposure. And so all we have to do is just look at these images, and we can see where the UV radiation is headed, just by its signature, essentially. Even though we're not seeing the light itself, we can trace out where it's going just by looking at where the low versus the high ionization regions are located. And so when we did that, we found that, in fact, for two of these galaxies, which are satellites of the Milky Way called the Magellanic Clouds, that, in fact, we are able to account for the ionization of the diffuse warm ionized medium by seeing that a lot of these nebulae were, in fact, transparent to the UV radiation. So we can explain the diffuse warm ionized medium that you see in this Edge-on galaxy, for example, that it probably behaves in the same way. That, in fact, UV radiation from these massive stars is managing to get out there into the interstellar medium of these galaxies and creating this warm ionized medium. Well, so if that's the case, then we wondered, maybe some of these ionizing photons, these ionizing particles of light, can actually get out of the galaxies altogether and ionize the intergalactic environment and perhaps even the universe itself. Because it turns out that the universe is ionized outside of the galaxies. So you remember the simulation that I showed you where we flew through the galaxy, and it turns out that all of that gas, well, a lot of that gas between the galaxies is in fact ionized. Here's a schematic of time through the universe. So the Big Bang is on the left, and the present day is on the right. And after the Big Bang cooled off and everything faded, the universe was neutral hydrogen, because the vast majority of all the atoms in the universe is neutral hydrogen, and back then there really was pretty much nothing else except a bit of helium. And so the universe was dark and just filled with neutral hydrogen everywhere. Well, then eventually some stars started turning on, and they were massive stars, and they were capable of ionizing some of this gas. They've essentially evaporated some of this neutral hydrogen by ionizing it. And so you start seeing patches of ionized gas, these purple patches in the midst of the neutral hydrogen. And then as more and more galaxies and stars started to form, you got so much UV radiation from these stars, it's thought, that essentially the universe became ionized. And so we transitioned from being totally neutral hydrogen, which is all dark here, to ionized hydrogen. And so the universe became transparent at these UV wavelengths that we see out here. And so today, the universe is essentially ionized. Well, we assume that it came from these massive stars. It's possible that the universe was actually ionized also by some of the accretion disks from supermassive black holes. We don't really know, but if we count up the black holes, we don't really see enough of them to explain the ionization of the universe. And so basically, we pretty much think that it has to have come from these massive stars. Well, if the universe was ionized by these massive stars and these primordial galaxies, then somehow those ionizing photons, the ionizing radiation, must have been able to escape from these galaxies. So that's something that we would like to be able to see today. So that's another thing that my group has been working on. Here is an image of the Small Magellanic Cloud, one of these satellite galaxies of our Milky Way. And we're trying to see now whether we can see the ionization structure for the entire galaxy. Now we're showing the low ionization species in red, which is still singly ionized sulfur. And we're showing the high ionization species in blue. And you can basically see that this entire little galaxy is bathed in an envelope of red, right? Meaning that very little ionizing radiation is escaping from this entire galaxy. There is one exception, and that's way over here. We see a naked blue region, which is the doubly ionized oxygen. So in that blue region, we might see the escape of ionizing radiation from this galaxy. Whether it's a significant amount or not is not very clear because we don't know how far it's going. It's not going to be a significant fraction of the radiation coming from this galaxy because it's just a small region, but nevertheless, it is a very interesting region. So the Small Magellanic Cloud doesn't have all that much star formation in it right now. It's not a very actively star-forming galaxy. It certainly has some stars forming, but it's not got a very high star formation rate. What would be more interesting to look at would be what we call a starburst galaxy. A galaxy that's forming stars at a rate that's so high that's essentially unsustainable. And that's what we have here. This is the galaxy M82, Messier 82. And this is a multi-wavelength image where you can see the hot X-ray emitting gas in blue in the center. That is shock-heated gas that has been heated by the supernovae of millions of these very, very massive stars. And it's driving essentially a super wind coming out from the center of that galaxy. So if all the stars are right in the center, in the nucleus of this galaxy, then that really concentrates all of this star formation, which is already at an unsustainable rate. And it's able to blow out, essentially, this wind, which creates a giant hole in the interstellar medium of this galaxy, therefore allowing you to also see all of the stars directly. They're not hidden behind gas anymore. So that means that essentially you would be able to have a lot of radiation escaping through those holes. So you can see essentially that the geometry of the starburst matters. We could have the stars all spread out, as we see in the top figure here, and that would be probably quite useful in helping you to get ionizing radiation out. But it might be even better to have all of the star formation concentrated in the center, like we saw in the galaxy M82 in the last picture. So I have another student who had just finished her PhD looking at these starburst galaxies. Here is one example where she had, in fact, discovered what's called an ionization cone in this galaxy. So here we have a high ionization species, in this case doubly ionized sulfur shown in red. And then we have a low ionization species, which is singly ionized sulfur, in blue. And you can see there's a lot of blue around here. It's looking pretty purplish and blue. But right here, along this line right here, you can see that it's very red. So here we see essentially the naked high ionization species once again in a cone that's emanating from the center of this galaxy. So that's suggesting that this galaxy, Arrow 10, is transparent along this particular line of sight, which, as you can see, is not pointed toward us. It's going off in this direction. So this is quite interesting because people had actually looked at this galaxy before and they had said, we've looked for the UV radiation and we don't see it. They just basically looked directly for evidence of that UV radiation and they hadn't seen it. Now we can kind of see why. It's because the cone is not pointed directly to our line of sight. The cone's pointed off to the side. And so that's why we can't see the stars directly. We can't see that UV radiation directly. But it doesn't mean that there are no ionizing photons escaping from that galaxy. They're just going off in a direction that we can't see. This is the ratio map that I showed you before. So this is more kind of what you've been used to looking at. The doubly ionized high ionization region shown in black, with the low ionization region shown in white. And so all of this is pretty much white, grayish white. This is noisy, so we don't really trust this. But here we can, again, quite clearly see the ionization cone that I was referring to. And Jordan Zastro is a student in the middle right here, whose thesis this was. She's now Dr. Zastro. Here's another example of a galaxy where she's found an ionization cone in this pink zone that you see over here. This is emanating from the galaxy out in that direction. These are all starbursts. Here's another one where she doesn't find it. Right here in this galaxy, you essentially see that it's mostly just blue. This galaxy is all ringed in blue, which is the low ionization species. So this galaxy, we would not expect to find an escape of ionizing radiation, even though it's a starburst galaxy. So another set of very interesting galaxies are called the green pea galaxies, and this is a thesis work from another student, Ann Jascott, who's right here at the Magellan Telescope. This is the site. The one that I showed you before is the actual telescope right here. So this is the telescope with which we took these data. These are the University of Michigan telescopes in Chile, state-of-the-art twin 6.5 meter telescopes. And this is the site in the foothills of the Andes in the Atacama Desert. So these green pea galaxies are particularly interesting because they're very compact. They're also starbursts. They're much smaller than our Milky Way galaxy, so they're very compact and forming stars at a very high rate and very small. But this green color is actually part of what's very interesting about them. Why? Because this green color comes from doubly ionized oxygen. And that, as I've mentioned before, is a high ionization species. These galaxies stood out from all the other galaxies in this survey of galaxies across the universe from their green color. And so if they are that bright in this doubly ionized oxygen, then I would suggest that they might be good candidates for the escape of ionizing radiation, because it suggests that they might be naked in the doubly ionized species. So we think that this is a galaxy that's very similar to these green peas. This is a much closer example where we can actually see some of its detail with the Hubble Space Telescope. And if you ignored the green color and took away the light from all of that doubly ionized oxygen, it might look something like this, where we see the red, again, from the ionized hydrogen, so you know that it's a vast star-forming complex, and you can see how blue it is. So that's all of the stars in the starburst going off in this little galaxy. This one's called Aro 11. And this one has been found by other people to actually be transparent in the UV. So what my student Ann Jascott has done is obtain some data from the Hubble Space Telescope. These are spectra now of just a handful of these green pea galaxies, maybe something like 5 of these galaxies, I believe, she's requested data for. They're still coming in, but we've obtained data for some of these already. And here we see a UV spectrum of one of these green pea galaxies. What she's doing now is she's looking for the signature of the low ionization envelope. So you remember, we already know there's a lot of the very highly ionized gas because they're green. They come from the doubly ionized oxygen. Now she's just looking to see if the low ionization zone is present. If it is, then the objects are opaque. If it's not, they're transparent. And so she's looking in particular for a low ionization species, which is singly ionized carbon, which should be appearing right here where this vertical line is. And if it was there, we would see an absorption line, very similar to this line that we see right here. This is a low ionization species, singly ionized sulfur, from our Milky Way galaxy, interstellar medium, right here. So this comes from our own galaxy. We do not see a similar signature here at all from the singly ionized carbon. And so therefore, we infer that this galaxy is indeed transparent to the UV radiation. So that's a very nice vindication of our suggestion that these green pea galaxies might actually be producing a lot of ionizing radiation, and therefore that they might be analogs of the kinds of galaxies that ionized the universe back when the universe was very, very young. Okay, so we've covered a lot of ground here. To summarize this, the ionizing radiation that's produced by massive stars can affect us on a very local scale right here in our own solar system. They also power the nebulae that are immediately in the vicinities of these massive stars, often just representing the remnant birth material out of which the massive stars formed. These stars are also capable of ionizing the interstellar medium, as we've seen, the diffuse gas that was at large distances from these stars, thanks to the transparency of the nebulae out of which they formed. And that we've even seen in these last few examples that the ionizing light from these massive stars could also be responsible for ionizing the circumgalactic medium and perhaps even the universe at the time of cosmic dawn. Thank you.